Okay, wonderful. So welcome to the Vantage seminar, everyone. This fall, we're having a series of talks on perspectives on Galois groups. And for our first talk, we're very happy to have David Harvader from the University of Pennsylvania. David was, in fact, my PhD advisor, so I'm especially happy to hear his talk today. And he'll be talking about an overview of the inverse Galois problem. So David, is it all right for us to video this talk?
Yeah, it's fine. Yep.
Oh, great. And if you have short questions, feel free to ask them during the talk. Okay, David, go ahead.
Okay, great. Well, thank you. Thank you for inviting me, and thanks to others for coming. So as Rachel said, the title is an overview of the inverse Galois problem. And being an overview, this will not be a talk that will go into details of the most recent results, but instead try to give the big picture. So let me start by beginning with the classical inverse Galois problem, which I'll abbreviate IGP, over the rational numbers, which asks, is every finite group a Galois group over the rationals? So we want to know, is there a finite Galois field extension L over Q with group G, given a group, if you're given a group G in advance? Well, this is something that people have thought about for more than a century. And Hilbert showed explicitly that the symmetric and alternating groups are all Galois groups over Q. Later, it was shown that all P groups are Galois groups over Q, and more generally, all nilpotent groups are Galois groups over Q. And the point there is one can construct covers by means of towers of field extension. So there's a little diagram to the right here. And the point is that at each step, you go up by say, an abelian extension, but each one is also Galois over the bottom, and so you can just go up in towers. It's much trickier for solvable groups because there, even though you can go up in towers, what happens is that successive extensions are abelian, but they're not Galois over the bottom. So it's much trickier. And so in the 1950s, Shafarevich had a quite intricate argument in a series of papers in which he did show that all solvable groups are Galois groups over Q. These days, if one wanted to follow that, this has been reformulated in terms of Galois cohomology. And if you're interested in taking a look, I would suggest looking at the book by Neuker, Schmidt, and Vingberg on cohomology of number fields. Well, what about other groups, in particular simple groups, where you certainly are not going to go up in towers at all? And so the various approaches have typically used Hilbert's irreducibility theorem, which I'll abbreviate HIT. So let me just say what that is. So let's suppose that you look at Q adjoin a bunch of transcendentals, and then you have a finite extension of that. So that's by the primitive element theorem, just given by one polynomial with coefficients in K, so rational functions in X. Then it says you can specialize the xi's to rational numbers, alpha I, in order to get a Galois extension of Q. So in other words, what you do is you, in the polynomial F, you replace every xi by the alpha I, and you get some extension L alpha. Now, if you just randomly pick something, you could be unlucky, and this might not even make sense, like you might be dividing by zero. Otherwise, another thing that could go wrong is you might end up getting something that's not a field. But what he's saying is there exists something. In fact, in some sense, which can be made precise in various ways, what happens is that it's true for most choices. So let me just give an example of that. So let's say you have Q of X and you join on a square root of X, so Galois with groups cyclic of order 2. If you replace X by a non-square alpha in the rationals, then you get an extension over Q. Q adjoins square root of alpha. Of course, if you took a square, that's not going to work. So it's not most in the Zariski sense, Zariski open sense, but it's most in some sense. So the point of this in terms of inverse Galois theory is that if we can find a G Galois extension of Q adjoin a bunch of variables, then applying Hilbert irreducibility, you get a G Galois extension of Q, a Galois extension of Q with group G. But in order to carry this out, we need to find extensions of Q adjoin a bunch of variables. So one early approach was the Noether problem, which said the following. Let's say you have a finite group G. So G can be embedded into a symmetric group Sn. So let G thereby act on a bunch of variables Z1 through Zn by permutation and take the fixed field. So you have this E, which is Q adjoins Z1 through Zn, the fixed field F. These are E and F are both transcendence degree n over Q. It's a G-Galois field extension. And the question is F purely transcendental over Q? If so, meaning that F is isomorphic to Q adjoins some algebraically independent elements x1 through xn, then we can apply Hilbert's irreducibility theorem and get that G is a Galois group over Q. Well, all right, so is it purely transcendental? So the first case is G being the symmetric group embedded into itself by the identity acting on Z1 through Zn. In this case, as we all know, the field of invariance is Q adjoins sigma 1 through sigma n, the elementary symmetric polynomials. Those are algebraically independent, so this is purely transcendental. So the conclusion is that Sn is a Galois group over Q, which we already knew, but it gives another proof. Let me say, by perhaps abuse of terminology, that the inverse Galois problem, IGP, holds for a field K if every finite group is a Galois group over K. Now, by the Hilbert irreducibility theorem, if you have inverse Galois over Q of x, you get inverse Galois over Q. So therefore, we'd like to understand Galois extensions of Q of x. So let's say you're given a Galois extension of Q of x, say E over F, which is Q of x, for example, taking a square root of x. And let's suppose that Q is algebraically closed in E, as in this example. Then you can base change your extension from Q to C, tensoring over Q with C, and then you get a field extension of C of x. It's still a field. It's still Galois with group G. This uses the fact that E, the original extension, and C are linearly disjoint over Q because Q was algebraically closed in E. So in this particular case, you would just get C of x, and then you would join on a square root of x there. Okay. Now, in this example, since we have an extension of C of x is the function field of the complex projective line, and then the other is a function field of another curve. So we have this actually then corresponds to a Galois branched cover of complex curves given by y squared equals x. And here's a picture of the x line. I have 0 and infinity, and it's branched over those 2 points, and it's unramified. In other words, étale over all the other points. Okay, so we have an étale, we have a branch cover that's étale away from finitely many points, the branch points. And now, if instead of using the Zariski topology, if we use the complex metric topology, this is actually a covering space over C minus the origin, or this P1C, or it's a sphere minus 2 points. Well, that is of course how we defined étale. We defined it so that that would work by the implicit function theorem. But anyway, so and it's Galois with group C2, which is to say that's the group of deck transformations of the topological covering. And more generally, anytime you have an extension of Q of x, which is regular over Q in the sense of Q being algebraically closed in it, then you get a G-Galois branch cover of the complex projective line, which can be viewed as a covering space of some U, which is the sphere minus points P0 through Pn, and where G, the Galois group, is the group of deck transformations of this cover. So what's happened here is we started with field theory, an extension of Q of x. We moved to complex algebraic geometry and then moved to topology. The question is, can we reverse this process in order to get Galois groups over Q of x, and hence over Q by Hilbert irreducibility, by means of topology? All right, so to do that, we first need to understand or recall how Galois topological covers work if you have the sphere minus some points. So in other words, what do I mean by a Galois cover? I mean that the group of deck transformations act simply transitively on the points of a given fiber over some point downstairs. Okay, so you have your U downstairs, S2 minus some points. You have its universal cover, and this is Galois with group pi1 of U. We have some finite cover of V to U with some group G. And so now the the fundamental group of V, which is the same as the Galois group of U tilde over V, is N, a normal subgroup of pi1 of U, and G is that quotient. What is pi1 of U? Well, it's the free group on N generators. You delete one point, you get the complex numbers or the real plane, and then you have to delete endpoints from that. Okay, so if you've given a U, which is S2 minus some points, then the group of deck transformations that you can get, that is to say the Galois groups, will be the finite groups on N generators, because they are the finite quotients of the free group on N generators. Well, okay, well, every finite group has N generators for some N, and so every finite group is then the covering group for some U. Now, that tells us on the topology side, we want to reverse the process and start with topology, go to complex algebraic geometry, and then go to field theory in order to get groups over Q of X and hence over Q. Well, the first step, going from topology to complex algebraic geometry, what we want to say is that if you have a finite covering space of the sphere minus P naught through Pn, and we think of the sphere as the complex projective line, then we want to say this actually is really induced by the forgetful functor from an étale cover of U, viewed as complex projective line minus those points. In other words, it's given by polynomials. To put it another way, there's a branched cover of the complex projective line with branch locus P naught through Pn, which gives you this cover by restriction to U. The fact that this holds is by Riemann's existence theorem. In fact, this is one way of saying Riemann's existence theorem. These days, we can think of it as following from Serre's Gaga, but of course, that's not how Riemann thought about it. Okay, so because of that, one can, if you have a topological cover, you can think of it as a branch cover of curves. And now the question is, how do you pass the field theory and get an extension of C of X? Well, first, of Q of X. Well, first, how about C of X? Well, you can take function fields, and so you have a finite extension of C of X, and we get that every finite group is a Galois group over C of X. We have IGP over C of X. But what we really want to do is descend to Q of X. So we would like to know, in this situation, if L is G Galois over C of X, is there an L naught over Q of X with that group such that this is just the base change? Right, and to say it geometrically, we're given something over the complex projective line with group G. It's unramified away from P naught through Pn. Is it actually induced by a G Galois cover of P1Q? Or in other words, can you define it by polynomials over Q? Well, this is given by polynomial equations over C. We wanted not just to send this cover, we wanted to send it with the Galois group, because otherwise you get an extension of Q of X, which might not be Galois, but becomes Galois over C, and that's not good enough. So we wanted to send the curve Y, the morphism phi, and all the automorphisms of Y over X corresponding to the elements of G. Well, all those things are given by polynomial equations over C. There are finitely many of them. And the question is, could you choose them all to have coefficients in Q? Well, for simplicity, I'm going to assume that the points P naught through Pn are Q points of P1. For example, Pj might be J. We could take Galois conjugate points, but let me just look at Q points. In this case, by a theorem of Grothendieck, which by the way fails in characteristic P, the cover and its automorphisms are all defined over Q bar. So the analog happens to be false in characteristic P. The proof actually uses topology, as is often the case when proving things over C or over other algebraically closed fields. Now, since all these polynomials I talked about have finitely many coefficients, and since they're all defined over Q bar, write everything, all the polynomials over Q bar, not just over C. And then they all lie in some number field. So we get a Galois extension of some number field, which induces the given extension of Q bar of X and then of C of X. And this number field K is called a field of definition of L over C of X, or of the corresponding cover. Well, what choices of K will work? And in particular, do the complex numbers, do the rational numbers work? Well, let's see, what would need to happen in order for it to have any hope of descending to Q? Well, if it did, then you could write the polynomials over Q. If we then take omega in the absolute Galois group of Q, Galois group of Q bar over Q, and you apply omega to all the coefficients of those polynomials, which remember now live in Q bar, then you get a new cover and apply it similarly to the polynomials defining the automorphisms, the elements of the Galois group. And what'll happen is, if everything was over Q, then nothing happened when you applied omega. And so we got back the same cover and the same automorphisms. Great. So if it's going to be defined over Q, it better stay the same when you act by something in the absolute Galois group. So I can write it this way. You have Y, you have the transformed cover, and you then have, these are isomorphic as covers and with the Galois group. So in order to determine whether this happens, we need to understand the action of the absolute Galois group of Q on the covers. Okay, so let's use what we know about the classification topologically of the covers. So if you take the sphere minus P0 through Pn, these are classified by the finite quotients of pi1. That's the free group on n generators, but more canonically, it's generated by A0 through An, whose product is 1. So here I'm including the generator associated to P0. And so what are the finite quotients? They are the finite groups together with generators G0 through Gn, whose product is 1. Okay, there's a technical point I need to mention, which is that this is actually for pointed covers, because pi1 is a base point. On the universal cover above it, you have a base point. Therefore, in each of the finite covers, you have a base point. What if you change the base point Q in the cover Y to some other point Q prime lying over the same point downstairs? So then there's an element in the group that takes one to the other, an element little g, and then the tuple G0 through Gn that had to do with the given cover gets uniformly conjugated by G. Each element is conjugated by G. Okay, so therefore, since I'm interested in covers and not pointed covers, to say that you have a G-Galois cover of P1 over C unramified away from P0 through Pn is equivalent to giving a group G a bunch of generators whose product is 1, that's what star meant, but modulo uniform conjugation by G. Okay, so this is the classification. Now, if you look locally at the covers, by which I mean looking at the complete local rings around the branch points and having a group act, then what one sees is that if you have this element alpha in the absolute Galois group of Q, if you have the given cover with data G and some little GIs, and the transformed cover G and some HIs, then the G's and the H's are conjugate by chi of omega, where chi is the cyclotomic character, tilde is conjugacy in G, or to say this a little bit more concretely, if the order of Gj we call Rj, and you look at the primitive Rj through divinity zeta Rj, and you see what omega does to it, it raises it to the Cj power, and then it's saying that Gj is conjugate to Hj to the Cj. Okay, so this is good because it tells us something about the how omega acts, but it's only a partial formula for y omega in terms of y, because to give y omega, you give this tuple up to uniform conjugacy, but we only know this up to individual conjugacy, and they might be conjugate for different j's, they might be conjugate by different elements. Right, so in other words, given what we know so far, there's a finite amount of ambiguity in determining y omega. And we would like to have a much better formula so we could be sure to know precisely over what number field this will be defined over. This is a big open problem. We don't know. But sometimes we get lucky, and it turns out that because of what group we have and which elements we chose, this ambiguity isn't there. And this is what's called rigidity. By the way, having nothing to do with the term rigid analytic space, which I'll mention later. Yeah, so let's say that we have a cover y to P1 over C, and you corresponding to G and some GIs modulo uniform conjugation. Let Ci be the conjugacy class of little gi, and now look at the following set, capital sigma, which you look at all the tuples H0 through Hn, which generate G, multiply to 1, and where each Hi is in Ci. Or equivalently, we can think of Hi being conjugate individually to Gi. So this includes all the possible descriptions of the transformed cover under the various elements of the absolute Galois group, and it may include other things as well. We'll say that G, together with the GIs, or the conjugacy classes, we'll say that that's rigid if all the elements of sigma are uniformly conjugate to each other, or are equivalently conjugate uniformly to G naught through Gn. Okay, so if that happens, then we'll say it's rigid. Suppose in addition, we also have this other next condition, which is let capital N be the order of G. And suppose that for every R, relatively prime to N, if you raise each element to the rth power, you get something conjugate to what you originally had. So another condition, which will not always happen. In that case, we say it's rationally rigid. Well, in that case, going back to what I said before, the partial formula for the transformed Y in terms of Y, if the original cover corresponds to G and G naught through Gn and the other G and H naught through Hn, we get that the G's and the H's are uniformly conjugate because of these two conditions. And so in that case, we get that the original cover and the transformed cover are isomorphic as covers and even with their Galois action. What that tells us is that the absolute Galois group of Q leaves the cover as a Galois cover fixed. And one says that Q is the field of moduli of the cover. Well, why was I discussing this? It's because we saw that in order for the cover to be defined over Q, it better be that the absolute Galois group leaves it fixed. So if these conditions happen, then the absolute Galois group will, then the absolute Galois group will leave the cover fixed. Does that mean it's defined over Q? One would like to think so. It's a little more complicated than that, but under some conditions on Q, for example, on G, namely, for example, if it has a trivial center, or if it's abelian, so the whole thing is the center. Under some conditions on the group, knowing that Q is the field of moduli actually forces it to be defined over Q. And so in that case, G is a Galois group over Q of X, and therefore over Q. So if we have all these things, then you get this group over Q. Now, it's natural to say, does this ever happen? Well, if it didn't, I wouldn't be talking about it. But I'll get into examples in a moment. Let me first mention, though, what happens if it's rigid but not rationally rigid? In that case, you still get that the cover is defined over Q zeta n, where n is the order of G under the above hypotheses. And in fact, even over a computable subfield of Q zeta n. And that's because the cyclotomic character doesn't, if you look at elements in the absolute Galois of Q zeta n, they don't do anything to zeta n. And so when you look at what happens with the cyclotomic character, you're fine. In particular, since it's defined over Q zeta n, it's defined over Q ab, the maximal abelian extension of Q, which of course Q with all the roots of unity adjoin the maximal cyclotomic extension of Q. Well, I mentioned before that the Hilbert irreducibility theorem holds over number fields. In fact, it over Q, that is, I said, but it actually holds over all number fields, and it holds over Q abelian and various other fields as well. These fields are said to be Hilbertian because Hilbert irreducibility holds. And so we get those groups as Galois, these groups that I'm discussing here that have all these wonderful hypotheses as Galois groups, not just over that field parenthesis X, but actually over those fields themselves. Now, as far as a little bit of history.
Could I ask you a question?
Yeah.
So why is it that in the case where you have rigid but not rationally rigid, that you get actually it defined over this field and not just
No. Well, that's what I said. Yeah, sorry. I said, okay, so I was sneaking into the word above, and above included the condition of having a nice center. Sorry.
Oh, okay. So
okay,
okay.
I was sneaking that in. Okay, but you're right. Otherwise, it would just be the field of moduli. And by the way, by a theorem of mine, even if you don't have a good center, at worst, if you would join on some root of unity, it'll be defined there. But that's not as good as being defined over the field you want. Okay, so some history. The notion of rigidity was defined in the early 80s independently by Bieli, Matzot, and Thompson. This followed related work of Xi and Fried. And this notion was then used to realize many finite simple groups as Galois groups over Q. In fact, even realizing them regularly. And so this gives evidence for the a regular inverse Galois problem, or RIGP, over the rationals, namely that the conjecture that every finite group is, in fact, a regular Galois group over Q. So you have some E over Q of X with group G, where Q is algebraically closed in E. Because the descent automatically preserves regularity because it was regular over C and over Q bar. In particular, as far as what people have achieved, among the 26 sporadic finite simple groups, they all are now known to be Galois groups over Q, except possibly the MAT2 group M23. In particular, the other simple MAT2 groups, M11, M12, M24, do occur, and so does the monster group, a group of order approximately 8 times 10 to the 53rd. This is the largest of the sporadic simple groups. And of the non-sporadic groups, these occur in families, and many of those have also been shown to be Galois groups over Q, mostly using rigidity. In particular, PSL2FP was shown by rigidity to occur for most P in the sense of the proportion being close to 1, at least. The rest were shown by another method, also using arithmetic geometry, by David Zuena. The thing is, how would you carry out these computations, for example, for the monster group? I mean, it looks hopeless to have these satisfy these conditions. And the answer is by character theory. So let me say something about that. So remember that if we have these conjugacy classes C0 through Cn and G, which are the conjugacy classes of our elements Gi, I defined a set sigma of H0 through Hn of elements that generate G, multiply to 1, and are in the respective conjugacy classes. Okay, and by the definition I gave can be rephrased as saying that rigidity holds if sigma consists of a single uniform conjugacy class under the conjugacy action of G. Let's, as above, assume that the center is 1, and so this in particular holds for non-abelian finite simple groups, which has been the focus of a majority of the attention in the case of this approach. In that case, it says that it's rigid if and only if the order of sigma equals the order of G. The point being that by the trivial center, G acts freely on sigma. So that shows that you have an inequality. And to say that acted transitively says you have equality. Now, sigma lies in an a priori bigger set, sigma bar, where you drop the generation condition. So, okay. So the order of sigma bar is at least that of sigma. And we also have this inequality. Putting those together, you get that if the order of sigma bar is the order of G, then sigma equals sigma bar, and they have the same order as G, and you have rigidity. Well, why is that helpful? Well, that's because there's actually a formula for the order of sigma bar in terms of character theory. And here's the formula, where I'm summing over the characters of G, and the GIs are as above. And this is, and this is the centralizer of GI. So that's the formula. I'm not going to give a proof. I'll give you references in a moment. But how would you use this? Well, the idea is you can compute involving this using the atlas of finite simple groups. So for example, for the monster group, rigidity and even rational rigidity, one can then see holds for the triple G1, G2, G3 of orders 2, 3, and 29. I should mention, by the way, that most of the examples with rigidity involve 3 elements, because even with character theory, it becomes pretty involved for more than 3. And most of the examples with more than 3 people obtained by doing it for 3 and then souping it up. And so therefore, lots of groups have been gotten regularly over Q. Weirdly enough, the solvable groups are not yet known to be regularly Galois over Q. We know they're Galois over Q, but we don't know you can achieve them by some regular extension using Q of X. That's an open problem. Okay, over Q abelian, more is known because there you don't need the rationality, just the rigidity, and in particular, all the sporadic simple groups occur over Q abelian. So for more detail about this, there are these books, and again, at the end, I have a list of references. Mala, Matzat, and Vogtlein books on inverse Galois theory, and Sayre's book, Topics in Galois Theory. Those are not totally up to date because there are newer results, but it summarizes what I said. And I guess at that point, there were actually 2 exceptions rather than 1 exception known over Q. Okay, well, let's go further than the inverse Galois problem, because one can ask more than just a yes, no. One is, what is the structure of Gal Q as a profinite group. Well, this group is infinitely generated as a topological group. And if the inverse Galois problem holds, then every finite group is a quotient. Unfortunately, knowing that does not determine the absolute Galois group. And the point is that if you had a topologically finitely generated profinite group, then it's determined by its set of finite quotients. But that's false for infinitely generated. You can have infinitely generated profinite groups that are not the same, but they have the same finite quotients. In fact, in this case, the opposite happens. Namely, on the one hand, if the inverse Galois problem holds for all number fields K, which is expected, then the groups Gal K all have the same set of finite quotients. But by a theorem of Neukirch, non-isomorphic number fields have non-isomorphic absolute Galois groups. So in fact, it would be the opposite of what we might hope for. Although on the other hand, one might hope for this in a different way, because this is related to Grothendieck's anabelian conjecture, which of course was formulated well after Neukirch's theorem, that says you can determine a number field by its absolute Galois group, and similar things in Grothendieck's conjecture. As far as what is the absolute Galois group of Q, it would be nice to have a conjecture in terms of generators and relations. There is no reasonable conjecture about it. There is a conjecture that it's isomorphic to what's known as the Grothendieck-Teichmuller group, GT, that was defined by Drinfeld and motivated by Grothendieck. But that group also is not described in terms of generators and relations, and we don't know its finite quotients either. So that wouldn't really help. Although it would be interesting to know this conjecture, because this field, this group GT hat, is closely related to the moduli space, fundamental group of the moduli spaces of pointed curves. So that would be interesting, but it wouldn't really help with inverse Galois. On the other hand, for Q abelian, there is a conjecture about the structure of Duda-Shafarevich, which is that the absolute Galois group is isomorphic to the free profinite group uncountably many generators. This is still open. There is a weaker form of it due to Iwasawa back in 1953, that if you, instead of looking at the absolute Galois group of Q abelian, you look at the Galois group of Q solved, the maximum solvable group over Q abelian, then that's isomorphic to the free prosolvable group uncountably many generators. Now, in terms of how you might even go about showing freeness, how would you show a profinite group is free? There's the following theorem of Iwasawa, that a countably generated profinite group gamma is free if and only if every finite embedding problem is solvable. So what does that mean? If you have a profinite group gamma, look at all surjections onto finite groups H with a surjection from another finite group G onto it, and the question is, can you complete this diagram with a surjection? This is a finite embedding problem and a solution, and this green surjection would be called the solution, or sometimes called a proper solution. Why is this called an embedding problem? It looks like it should be called a lifting problem, but it's because of Galois theory. Namely, if gamma is the absolute Galois group K, then it asks whether every H Galois extension of K embeds in a G Galois extension. So that's the point for that terminology. So the theorem was, again, that for a countably generated profinite group, it's free if and only if every finite embedding problem is solvable. And that's how you would go about proving freeness. There are lots of other questions one can ask in terms of the fine structure. Which finite groups are Galois groups over Q if we specify in advance which primes can be ramified? So unlike inverse Galois, the answer is not going to be all. It'll be some. Which ones? That's quite interesting. It's quite open. There's a conjecture of Boston and Markin that if the abelianization of G can be generated by D elements, then G is a Galois group over Q ramified at D primes, possibly including infinity. It's also a complementary conjecture of mine, which says that there's some constant such that for every positive integer, if you have an extension of Q ramified just at primes dividing n and maybe infinity, then G can be generated by at most log n plus C elements. I'd originally actually assumed tamely, because the analog of this is actually true for global function fields. And there it's only true for tamely, it's false otherwise. But a student of mine, Ben Pollack, gave evidence for this conjecture, which turned out to include examples even in the non-tame case for certain kinds of groups, like nilpotent groups and some others. So maybe it's true without that. There's also partial results on which finite groups can be Galois groups. This had to do with how many generators, but which ones, there was meticulous some results of mine and former students of mine and other people, but it's very partial. And in general, it's mysterious. Okay, well, what about inverse Galois over other fields than ones I've talked about? Well, the various things I already said suggests a conjecture, namely that the regular inverse Galois problem, RIGP, holds over all fields. That for every field K and every finite group G, there's a G Galois extension of K of X, in which K is algebraically closed. So we saw this is true for C and for Q bar, and we expect it to hold for a number of fields and for Q abelian. Now, if the irregular inverse Galois problem holds for a Hilbertian field, then you can specialize and it holds for K. Of course, that's false if it's not Hilbertian. RIGP holds over C, but of course, you don't have Galois groups over C. It's not Hilbertian, you can't specialize. Well, what about the regular inverse Galois problem over a finite field? Well, then we're looking at the finite field parenthesis X, and that's analogous to a number field. So based on the above expectations, we would anticipate that RIGP would hold. And based on our experience, this should be easier to do than proving it for number fields. It's still open. I must say that a long time ago, I thought that by now it would have been proven, that this at least would have been proven, but it's still open. There is a weak form of this, actually, which is kind of amusing, which is for every finite group G and every for every finite group G, there is some positive integer n, such that your group G is a Galois group over K of X for every finite field of more than n elements. This was proven by Florian Popp, and just before that, there was a variant which restricts the characteristic of the finite fields, proven by Fried and by Yarden. And key ingredient is the Bay bound on the number of points on a curve over a finite field. Well, what about regular inverse Galois problem over other fields? For example, how would one generalize what the fact that we know it for C? And as a hint, in some sense, is, well, C is algebraically closed and it's complete, so maybe those help. So there's a theorem of mine that says that if K is algebraically closed, or if it's complete, well, a complete discretely valued field, then the regular inverse Galois problem holds for that field. So this generalizes it for C. So it says in particular, we have regular inverse Galois problem for FP bar, because that's algebraically closed, for QP and Laurent series over a field, because those are complete discretely valued fields, and others. And actually, the way I stated the theorem is a bit more general. It is also true for the fraction field of any complete local domain that's not a field. So it doesn't actually have to be a complete DVR. So, for example, Laurent series in two variables, meaning the fraction fields of fraction field of Laurent of power series in two variables. Okay, so let me just sketch describe the idea of the proof. So there were two cases, algebraically closed or complete. In the complete case, let me just phrase it for QP, just for ease of description. Given G, we want a G Galois branch cover of the p-adic line. So we can do that locally in the p-adic topology so that it's locally cyclic, meaning locally it's given by a disjoint union of copies of some cyclic cover. Those are easy to build. And make them in such a way that the local covers agree on their overlaps. For example, make them trivial on the overlaps. Now patch them together p-adic analytically to get the desired cover. Now, how do you patch them together p-adic analytically? One method is to use Grothendieck's theory of formal schemes, which had been motivated by much earlier work of Zariski. Another approach is to use the theory of rigid analytic spaces, which was begun by Tate and then with later work by Raynaud and many others. So that's the idea in the complete case. As far as the algebraically closed case, how do you get regular inverse Galois over an algebraically closed field? Well, take the Laurent series over it, call that capital K. By the complete case, we have the result for capital K, so we have a regular extension of K of X, capital K of X. And the equations that define this and the group action involve only finitely many elements of capital K, finitely many Laurent series. So therefore, the whole thing is defined over something something of finite type. You take a finitely generated little k subalgebra of capital K, call that A, and you have some extension of that, which is generically G Galois. This should be over A of X, or over the A line. And so if you take spec and you let V be spec A, we get a G-Galois branch cover of P1A, which is P1K cross over K with V. K is algebraically closed, so there are loads of K points. Pick a suitably general K point, take the fiber of P1 cross V over that point of V, and you get something over P1. And because we can choose that suitably generally, it can stay G-Galois connected. And that's how that works. Okay, so therefore we have regular inverse Galois over complete and algebraically closed fields. Now, where did we really use algebraically closed? It was to get K points. And to be a little bit more precise, every smooth K variety with a K point has infinitely many K points. You need to stay away from some points because those will be bad. Those might have bad specializations. Now, Florian Popp called a field large if it has this property. Some authors use the terminology ample for these fields. This includes algebraically closed fields. It includes the reals, the p-adics, the totally reals, other fields such as the totally p-adic algebraic numbers, and so forth. And as a result, what he obtained was that the regular inverse Galois problem holds for large fields. And actually, he showed more than that. I should mention that the case of the real numbers was shown much earlier in a joint paper of Kroll and Neukirch. Okay, now, what about the structure of the Galois group of K of X as a profinite group? To get back to something I discussed before in a slightly different context. Over the complex numbers, it's known to be a free profinite group of uncountable rank, in fact, equal to the cardinality of C. And this was due to Duas D. And the rough idea is that the Galois extensions of C of X correspond to Galois branch covers of P1C where you're not specifying the branch locus. If you specify the branch locus, say P0 through Pn, then let P0 be infinity, then its generators A1 through An corresponding to the complex numbers at which P1 through Pn lie. In the limit, when you don't specify, what happens is that, well, for each individual S, the maximal extension ramified only there is the free group on those generators. Take the inverse limit of these free groups, and roughly speaking, you're going to get the free profinite group on all the elements of C. So that's the rough idea of why this is true. Well, what about the absolute Galois group of K of C for K of X for other algebraically closed fields K? Well, in characteristic P, this wild ramification, and because of that, the Galois group of the maximal extension ramified just at a given finite set S is not free. So therefore, we would expect the absolute Galois group of K of X to be a limit of these non-free groups in characteristic P, and therefore, why would we think that they should be free? Nevertheless, there was a theorem that Florian Popp and I independently proved, which says that if K is algebraically closed, even if it's characteristic P, then the absolute Galois group is a free profinite group on capital K generators. On the cardinality of capital K generators. And the proof involves passing to the Laurent series field, as before, patching in the t-adic topology, and solving embedding problems to obtain freeness. So the idea is use Iwasawa's theorem. Problem is, Iwasawa's theorem assumed that it was countably generated, and if you had an uncountable field, then it would, if it were free, it would be uncountably generated. So we need a more general result than Iwasawa's. So there's this following theorem of Melnikov and Chatsidakis, which says that if you have a profinite group and an infinite cardinal M, then gamma is free of rank M if and only if every non-trivial finite embedding problem has exactly M solutions. So, and that turned out to suffice, and that gave the result. So that tells us that over any algebraically closed field, the absolute Galois group is free. It's a mystery, though, as to what the generators are. So you remember over C, the generators corresponded to the points of C. But here, let's say you have the line over some field K. The generators do not correspond to the points of K, because otherwise, if you had a finite set, you'd get freeness, and you don't. So this is mysterious. It would be nice to have some geometric interpretation of these generators. In the case of FP bar, what the freeness result says is that the absolute Galois group of FP bar of X is free of countable rank. Now, FP bar of X is the maximal cyclotomic extension of FP of X, because FP bar is FP with all the roots of unity thrown in. FP bar of X is analogous to Q. So this field is analogous to the maximal cyclotomic extension of Q, which of course is Q abelian. So to say that the absolute Galois group is free in this situation is analogous to saying that the absolute Galois group of Q abelian is free. So one could think of this as more motivation for Shafarevич's conjecture, or one can think of this as a proof of the geometric analog of the Shafarevich conjecture. Also, instead of talking about maximal cyclotomic, we could talk about maximal abelian. And in fact, if you took the maximal abelian extension of FP of X, its absolute Galois group is also free, and this was a result of mine. Now, what about if you prescribe the ramification? Well, as I said, for Q or for number fields, it's very fragmentary. Somewhat more is known in the case of FP of X or other global function fields, but we actually have a solid answer in the case that capital K is little k is algebraically closed, and you're over little k of X. Well, let's first of all talk about C and let S be P naught through Pn as before. Then the finite Galois groups over C of X, ramified just at S, as we discussed, are the groups on at most n generators, because the topological fundamental group is free of order n, and we pass from topology to complex analysis to Galois theory or field theory. More generally, if you had any smooth projective curve X of genus G may be positive, and you have some points there, then what's pi1 of X minus S? Well, by topology again, it's free of rank 2G plus n, and so by the same kind of argument, the finite Galois groups over C of X that are ramified just over S are the groups that can be generated by 2G plus n elements. So there we know the answer, and that's what it is. What if K is algebraically closed of characteristic 0, but not necessarily C? The same conclusions hold, namely it's still 2G or 2G plus n, depending on the genus. This was shown by Grothendieck near the end of SGA1 by relating the algebraically closed field K to C, using the fact that both K and C are algebraically closed of characteristic 0, and then you use the result for C, and one could get it that way. But what if you're in characteristic P? Well, then it's false. It's not true that the groups you get are the groups on 2G plus n generators, and that's it. And the simplest example is to take P1 with n equals 0. So we're just deleting, say, the point at infinity, and so we have the affine line. There's a non-trivial Galois unramified cover of U, the affine line, given by y to the p minus y equals x. That's an Artin-Schreier cover. So one can say that the affine line is not simply connected in characteristic P over an algebraically closed field. This cover has group cyclic of order P. And so, but in fact, every finite P group is a Galois group over Q. Somewhat easier to see is every elementary abelian P group is a Galois group over U by just by taking X and then something times X, something else times X, etc., different constants, independent over FP. So you can have as many generators as you want. So that conjecture is false. So what groups should occur over the affine line over an algebraically closed field of characteristic P? And more generally over U, the complement of a finite set inside of a smooth projective curve of genus G over an algebraically closed field of characteristic P. Well, in 1957, Abhyankar conjectured that if you have a smooth projective curve of genus G over an algebraically closed field of characteristic P, and you have a finite set S, of element points P naught through Pn, then the answer is the following. He said that the finite groups that are Galois groups of unramified covers of U are precisely those such that every prime to P quotient of G can be generated by 2G plus n elements. So it's not G itself, but every prime to P quotient. And that does not contradict the examples I just gave with Artin-Schreier covers. In particular, in the case of for the projective line at n equals 0, it says that if you take the affine line, then the Galois groups that you get are the quasi-P groups, meaning the groups with no prime to P, no non-trivial prime to P quotients. Equivalently, it's the groups that are generated by their P subgroups, or if you like, by their CELO P subgroups. Well, the case of the affine line was proven by Raynaud using rigid patching, and then I proved the general case using what he had shown and using formal patching. Afterwards, by the way, Florian Popp showed that using rigid patching, one can also basically restructure the proof and so phrase it that way. And in addition, you can even get more, he showed. additional properties. So we know, that means we now know the finite Galois groups over affine curves in characteristic P over an algebraically closed field. But again, we can ask, what's the structure of the Galois group with the maximal extension around that's ramified only at S? This is a profinite group. It's often written pi1 of u. It's the étale fundamental group. And the difficulty is that this is infinitely generated in characteristic P, unlike characteristic 0, because of wildness. The tame fundamental group is finally generated, but the full fundamental group is infinitely generated. So knowing the finite quotients doesn't tell us the group. And in fact, the conjecture is that the opposite happens, that, again, motivated by the Anabelian conjecture, although not covered by the original Anabelian conjecture, which says that pi1 of u in this situation determines u, and in particular determines k, because u, remember, is a curve over some algebraically closed field k. Well, just a little bit is known, namely the following theorem of Tamagawa, which is, so let's say you have your u over an algebraically closed field k, but let u naught be the affine line over fp bar. If pi1 of u, the groups you get over u, are the same as those you get over u naught, then u and u naught are isomorphic as schemes. So that would be consistent with this, but we don't just want to relate u to u naught, we want to relate u to u prime for any two u and u prime. But unfortunately, this remains open, and people don't really see what to do. Well, that's it, except here are the references that I mentioned, the reference books, and thank you very much.